Here we are in the last section of the chapter, and it could be very long, but I want to keep these videos short, so let me just give you the high points. Real systems are often not at standard conditions. Standard conditions are things we find in our textbook. In the real world, we will see real things, and so really we will work a lot more with Q outside of the college classroom. And that gives us a new equation. We have our delta G0 for what we have for standard states, but now what we have is this correction factor, where R is the gas constant with terms of units of energy. We have T in terms of Kelvin, and we're using what we taught you in chapter 15, the reaction quotient. So yes, this is an equation, and what I want to do is work through a real-life example. So sample exercise 1911, it has you walk through an example of using this equation. It says calculate the delta G, the term on the left. They give you a mixture of nitrogen, hydrogen, and ammonia. You do not know if it is at standard state. You do not know if it is at equilibrium. So what you do is you check it out. To find the delta G0, well, that would require, because this is in the textbook, you to look up the numbers. And you would say 2 times the delta G0 for ammonia, and you would subtract from that the reactants, 3 times the delta G0 for hydrogen, and you would add to that the delta G0 of nitrogen. Now, in the back of the textbook, you can see that this is a negative 16.66, and maybe you'll remember that for the elements, the delta G zeros are 0. You would also see zeros in the column. This gives you a delta G0 of negative 33.28 kilojoules. So we check off, we've got our delta G0. We also have to calculate our Q, and that will be the pressure of ammonia squared divided by the pressure of hydrogen cubed times the pressure of nitrogen. So we'll pop in our numbers. We have a 0.50 squared on the top. We have a 3.0 cubed on the bottom, and we have a 1.0 also on the bottom for our nitrogen. It gives us a Q of 9.3 times 10 to the minus 3. Now, I spoke quickly because I really don't want to make these videos too long, so I apologize. Now what I'm going to do is put it into the delta G equation. I have my delta G0 of minus 33.28 kilojoules. I will then add to that the correction factor. R is the gas constant in energy units, 008314. I'll leave off units just so it fits nicely. Our temperature has to be in terms of Kelvin, 298. And then we have the ln of 9.3 times 10 to the minus 3. This correction factor, it turns out to mathematically have a value of negative 11.6. So our delta G for this process is a minus 33.3 minus an 11.6, and we come out with a negative 44.9 kilojoules. That tells us that the reaction to form ammonia under these specific conditions is spontaneous in the forward direction. So those are the kind of decisions you will make as you work problems. Okay, second last one on here, where we actually talk about something. We have to say, after close to a full year of Gen Chem, things are finally beginning to come together. So we have the correction equation, and we say at equilibrium, if it is at equilibrium, our Q is equal to K, and also at equilibrium, we have a delta G equal to 0. I left that out because I wanted you to think as we did this. So if we have 0 is delta G0 plus RT ln K, we can rearrange this equation And now we have a relationship between delta G0 and K. The first one that's listed there is the easy one. I can easily type that in. The second one, it says that K is e to the minus delta G0 divided by RT. Please do some practice with your homework problems. These kind of questions are going to be on the midterm, and you'll have to crunch through your numbers. So in the middle, I guess I kind of got covered. I just didn't want to make another slide about this. Since we now know about delta G, we can now see the correlation with K. So another way of saying this is knowing K, we now know delta G, or knowing delta G, we now know K. I could have gone on and on and on, but what I want you to do is take a look at this table. Notice what is on the right-hand side for K. All of these are going to favor the reactants, and notice the delta G's are positive. That means the reaction is not spontaneous as written. We are going to sit on the reactant side. Notice that at 1, our delta G is 0. That is equilibrium. We set that as a standard for this system. And then look what happens as we go in the other direction. When the K is positive, we know we're going to favor products. And notice all the delta G's are going to be negative. Again, there may be a word question. I'm going to try to work some out for you. But again, this is the lecture. This is going to allow you to actually explain solubility. This would be too long. So what I'll do is I'll make a separate little video and post it online, and it helps you see why sodium chloride can dissolve whereas silver chloride does not. Silver chloride has a KSP. We can calculate these delta G's. We can see why they're different, and we can look at how they change with temperature. So everything you've seen in this course really comes together in the chapter. And as a final parting shot, coming up is the chapter on electrochemistry, where we will talk about the E0. At this point, you know about delta G and you know about K. So, one chapter left to kind of wrap things up. I do not know if we're going to cover everything as we're online, but this chapter on thermo and the next chapter on electro are really, really important for your upper level courses.